Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on August 13, 2025, about 6 days ago. The standout finding is that learning from robotized human videos boosts bimanual kitchen task success from 12% to 74%, roughly a 5 to 6 times improvement, with only 50 real robot demonstrations per task. The paper is titled, Masquerade, Learning from In-the-Wild Human Videos Using Data Editing. And as we will see later, the implications for data efficiency are quite significant. By editing egocentric human clips to look like robot views, the method pre-trains and co-trains a policy that generalizes to unseen scenes. Building on that, commenters highlight robotizing human kitchen clips, emphasize no real robots in the videos, and praise the creative use of epic kitchens for strong generalization. Engagement looks solid, with one post around 120 likes. Alright. This overview figure walks through the pipeline end to end. On the left, raw egocentric human kitchen clips are transformed into edited videos, where the human arms are removed and a twin-arm robot is overlaid, matching the recovered hand trajectories. Moving to the center, those edited clips pre-train a vision encoder and then co-train with a small single-scene robot dataset through the DiffusionPolicy head. On the right, the learned policy executes zero-shot and new scenes, handling varied layouts and backgrounds. Okay, let us zoom into the full diagram first, since it maps the whole journey from human clips to deployment. On the left, the editing block shows raw egocentric video, then extracted hand poses, hands inpainted, and finally a virtual two-arm robot overlaid to match motions. Next, the center flow feeds edited videos and a small robot dataset into a vision transformer in DiffusionPolicy, with a 2D keypoint auxiliary loss. Finally, the right column illustrates successful rollouts in new kitchens. Next, this scene grid clarifies the evaluation setup. The left column shows the 3 bimanual tasks, while the center column presents the training scenes in distribution, and the right block lists 3 out-of-distribution scenes per task. You can see object layouts, table mats, and backgrounds change substantially on the right, which stresses generalization. The rows correspond to stack pots, scrape potato, and sweep chilies, with consistent viewpoints to isolate scene shifts rather than camera changes. Now these side-by-side bar charts quantify the jump in success. On the left, success rates across stack pots, scrape potato, and sweep chilies show the blue method towering over ImageNet, Dino V2, and HRP, landing around 70 to 80%. On the right, the ablation bars reveal why. Removing the robot overlay or stopping co-training slashes success, while keeping both delivers the highest averages. The error bars indicate variability, and the consistent gaps highlight strong generalization. Shifting to the appendix table, we get the concrete training setup that powered the results. On the left, the vision encoder is a VT base with 86 million parameters, trained at 224 by 224, batch 160, learning rate 1 × 10 to the -4, using Atom W for 150,000 steps. On the right, the DiffusionPolicy matches the input size, uses batch 64, the same learning rate, Atom W, a cosine schedule with 500 warm-up, and 40,000 steps. Continuing from the training details, 2 takeaways stand out. Explicitly robotizing human videos closes the visual embodiment gap and delivers 5 to 6 times higher success with only 50 real demos per task, and keeping the 2D keypoint code training during fine-tuning is crucial for generalization. Thanks for listening. I am Alex, signing off.